Hi everyone, thank you for coming. My name's Paul Malin. I work for Activision Central Tech as part of a small team based in the UK. I helped to implement some of the color pipeline for high dynamic range display in Call of Duty WWII, developed by Sledgehammer Games. And while doing this, I learned a lot. I'm hoping I can share some of what I learned with you today. I'm going to focus on some of the foundational concepts and things that I found particularly useful or interesting. HDR displays really do look great, but HDR is currently only available for a small percentage of consumers. So why is this stuff useful to know? Well, adding HDR support can touch many areas of the graphics pipeline. It's good to know how the area that you're working in might affect the HDR version. And also, I'm guessing that someday this will be the standard display technology, so it's good to be familiar with what's coming. To start with, I'm going to recap some color science background material. When dealing with color spaces, or skipping the less interesting chapters of a graphics textbook, we often see this diagram. But what is it? And when converting between color spaces, we use 3x3 matrices of magic numbers. So what are those numbers, and how are those calculated? This might not be the most thrilling topic. There are lots of graphs, and I'm going to go into more detail than you need to know to implement HDR display. But as the physicist Richard Feynman said, everything is interesting if you go into it deeply enough. Well, we'll see about that. So let's start at the very beginning. A long time ago, roughly a nanosecond after the universe was created, what we call electromagnetic radiation came into being. Electromagnetic radiation travels as waves in discrete packets of energy called photons. There are a ridiculous number of photons flying out of the sun and other lights, bouncing around and generally making graphics programmers unhappy. Every photon has a frequency that's dependent on the amount of energy that it carries. Electromagnetic radiation travels at the speed of light. Given this speed and a photon's frequency, we can calculate its wavelength. The full range of wavelengths or frequencies that electromagnetic radiation can take is the electromagnetic spectrum, from short wavelengths such as gamma rays and X-rays to long wavelengths like microwaves and radio waves. Light is what we call the visible or near visible range of the electromagnetic spectrum. Our eyes can detect wavelengths in approximately the range 380 to 780 nanometers, where a nanometer is a billionth of a meter. This range is the visible spectrum. Any light we observe contains a distribution of photons with different wavelengths all mixed together. This distribution is the light spectrum. If we shine light through a prism, we see chromatic dispersion, where each wavelength is refracted to a different degree. This lets us see the light spectrum. We can represent the light spectrum as a spectral power distribution, showing the intensity of light for each wavelength. So the white line at the top represents how strong the light of each wavelength is. In this case, there are lots of reds, fewer yellows and greens, and not much blue. When we mix these all together, we see the orange color at the bottom. Of course, we see light with our eyes, and different spectral distributions appear to us as different colors and intensities. A typical person's eyes will have 3 types of cone receptor cells that respond differently to different wavelengths of light. This is called trichromatic vision. The 3 receptors are called the L, M, and S cones, after the long, medium, and short wavelengths that each one most strongly responds to. This is a normalized plot of spectral sensitivity, showing how strongly each cone responds to different wavelengths. So let's take this spectral distribution. We can see how this gets weighted by the sensitivity of each cone. The area of each shaded region is how strongly each cone will respond to this particular spectrum. As the brain only receives signals from 3 types of receptor, it turns out that we can represent the perceptual result of seeing any spectrum with just 3 values. This also means that we can perceive what looks like the same color from various different spectral distributions if they produce the same 3 resulting values. We also perceive the brightness of light with the same power, but from different parts of the spectrum differently. Red and blue shades appear darker than green shades with the same power. This perceived brightness can be represented as a luminosity function that describes the perceived brightness of different wavelengths. When specifying intensity, if we're measuring the amount of electromagnetic radiation directly, we are using radiometric units. Often, intensity will be weighted by the luminosity function to represent how bright something would appear. When we're doing this, we are using photometric units. In order to find out more about light and color vision, for a long time, scientists have performed color matching experiments. The first of these was in 1850 by James Clerk Maxwell. In these experiments, a test color is projected onto a white screen, and subjects try to match the appearance of this by adjusting several other colored lights shone on top of each other. Towards the end of the 1920s, a pair of scientists, William David Wright and John Guild, independently conducted a series of these experiments. A subject would look through holes in a screen. Behind the screen, on one side, a test color made of monochromatic light of a single wavelength was projected onto a white screen. This would be matched by dialing knobs that would adjust the intensity of monochromatic red, green, and blue lights. Sometimes the test color could not be matched by mixing these lights. To account for this, the dials were ranged from -1 to 1, and dialing a negative value would add a light of that control's color to the test patch. The results were obtained for various frequencies of visible light and averaged from several observers. These results are called color matching functions. Although these functions only represent results for individual wavelengths of light in the spectrum, due to the additive nature of mixing light, with these results, we can actually match the perceived color of an arbitrary spectrum. Again, if we take a spectrum and we multiply the spectral intensity at each frequency by the color matching curve values for that frequency, and then we integrate or add up the resulting values to give us the area under each graph, this will give us 3 values, which we can use to dial the controls in the color matching experiment to produce a patch that would look the same as the color that we are trying to match. In 1931, the CIE, the International Commission on Illumination, proposed a set of standards for measuring color based on these results. This table of results is the CIE 1931 Standard Observer. We can take the CIE RGB color matching functions and plot them in 3D if we treat R, G, and B as coordinate axes. For each wavelength of light, we can take the R, G, and B value from the color matching functions at that wavelength and use these 3 values to plot a point in 3D. The curve this traces is called the spectral locus. We can represent light of various different intensities by scaling this curve towards and away from the origin. By projecting the spectral locus to the origin and extending it to infinity in this way, we can represent a surface for the various wavelengths of monochromatic light at various intensities. The volume of space contained inside this surface represents all the possible colors that we can perceive by mixing light of different wavelengths. This is the CIE 1931 RGB color space. It's defined by the table of values that formed the RGB color matching functions. In the CIE RGB color space, the color matching functions can have negative values along the red axis. The CIE also introduced another color space, XYZ, derived from the RGB color space by a simple affine transformation, or 3x3 matrix multiply. This XYZ color space has a number of convenient properties. Firstly, the values in the XYZ color matching functions are all positive. We mentioned earlier how we perceive light of different frequencies with different luminances. In the XYZ color space, the y-axis was carefully chosen to match the luminosity function. So values with a bigger y-coordinate, up in this visualization, appear brighter. This is the CIE 1931 XYZ color space. In the RGB color space, the axes represented specific physical wavelengths of real colors. In the XYZ color space, the axes no longer have a physical meaning, and X, Y, and Z are called imaginary or hypothetical colors. Again, it's the table of values for the color matching functions, this time X, Y, and Z, that define the XYZ color space. Sometimes we're only interested in light's chromaticity. This is its hue, or the color that it appears, irrespective of intensity. Typically, we represent this by projecting a color in the XYZ color space onto the plane X plus Y plus Z equals 1. This chromaticity color space is the badly named lowercase xyz color space. As these are points on a plane with the relationship x plus y plus z equals 1, we only need 2 of these values to specify a chromaticity, as one value is redundant and can be calculated from the other 2. Typically, z is dropped, allowing us to specify a chromaticity as just x and y. Sometimes, as well as the projected xy chromaticity coordinate, we also keep the big Y coordinate from before projection so that we can reconstruct the full XYZ coordinate if needed. The XY projection is the CIE 1931 XY chromaticity diagram that we had a glimpse of earlier. This is a map of all visible colors irrespective of their intensity. The horseshoe shape corresponds to colors of light at specific wavelengths, the spectral locus. The area that it encloses represents all the colors we perceive from mixing different wavelengths. It's another deliberate property of the XYZ color space that the XY chromaticity diagram gives us chromaticity coordinates in the 0 to 1 range that are all under the line x plus y equals 1. This CIE XY color space is commonly used as a standard with which to specify other color spaces. For an arbitrary RGB color space, its color primaries are often specified as XY coordinates in this CIE XY color space. The color primaries tell us what the primary colors red, green, and blue in our new color space map to in terms of real-world chromaticities. Shown here are the srgb color primary XY coordinates. As these XY values just tell us about chromaticity and not intensity, these color primaries are effectively giving us direction vectors in the XYZ coordinate system. However, the relative lengths of these vectors is not specified by just the primaries. Often, for an RGB color space, a fourth XY coordinate, the white point, is defined. If we add together the red, green, and blue primary vectors, we could end up at any point in the color space, depending on their lengths. We can scale their relative lengths without affecting their direction, so that when they're stacked, they end up at the white point. In this way, the white point is simply defining the relative lengths of the color primary vectors. Now, if we specify a color of 1, 1, 1 in our new color space, it will end up with a chromaticity at the given white point. Typically, the overall scale of the primaries is defined so that the white point produces a luminosity, the big Y coordinate, with a value of 1. In this way, we've defined our new RGB color space within the XYZ color space, indexed by 3 values, with axes along the color primaries, where a value of 1, 1, 1 will have a chromaticity at the white point and a luminosity of 1. In this example, we're showing the srgb primaries and white point. Colors within this volume are part of the srgb gamut. So we've seen how, given XY coordinates for RGB primaries and the white point, we can define a new color space. But if you want to use this color space, we need to calculate the scale factors for the length of the red, green, and blue primaries. To do this, we can turn color primary chromaticity XY coordinates to XYZ vectors on the plane, and then use these as basis vectors in a matrix. These are the scale factors we want to find, that multiplied by this matrix will take us to the white point. Rearranging this, we can get those scale factors if we just multiply the white point by the inverse of our matrix. Finally, we adjust our scale factors to normalize the white point y-coordinate. So now we can apply the scale factors that we've calculated to our primary vectors to get the final 3x3 transform that will convert from our new RGB color space into the XYZ color space with the correct primary vector scaling. By inverting this matrix, we can perform the opposite transformation from the XYZ color space to our new RGB color space. In this way, by using XYZ as an intermediate, we can multiply matrices together to convert from one arbitrary color space to another. Typically, we might calculate all our color transform matrices offline and store them as constants. As the y-coordinate in the XYZ color space represents luminance, the middle row of the matrix that transforms to the XYZ color space actually holds the luminance coefficients for our new RGB color space that we can use to calculate the perceived intensity of a color. Sometimes we use color temperature to specify a color. This is based on the physics of black body radiation. A black body with constant temperature emits light with a specific spectrum. Hot things glow red hot. Then, as they get hotter, they glow yellow, then white, and then blue. The relationship between temperature and the resulting color is very specific, so we can use a temperature in Kelvin to specify certain colors. We can plot this color that objects at a certain temperature glow as a line on the chromaticity diagram. This is called the Planckian locus. It's common for natural lights to have a spectrum similar to blackbody radiation, so color temperature is sometimes used to specify the color of lights. Some color spaces use this to define their white point, and a number of these are standardized. This is standard illuminant D65. 65 as it represents a color temperature of approximately 6,500 Kelvin. To measure the brightness of an image, we use luminance. This is a photometric intensity value irrespective of the area of the surface we're looking at or how big the surface appears in our field of view. We measure luminance in candelas per square meter, also termed nits. When we use the term dynamic range, we're describing the range between the lowest value and the highest value that we can represent. Typical real-world light intensities have a very high dynamic range. An LCD monitor is around 250 nits, a fluorescent lamp is around 12,000, and the sun can be as bright as 1.6 billion nits. When we work in a color space that has curves proportional to these real-world values, it's called a linear or scene-referred color space. So if the sun is 1.6 billion nits and an SDR screen is 250, we need to do something to compress this range for display. Taking an HDR scene-referred image and processing it to be displayable is what we call tone mapping. This is a similar process to what happens in film or photography. Tone mapping is a new term, but really artists have been thinking about light and color and reproducing realistic images with just paint on canvas for a very long time. Our eyes are amazing for processing the real world, but they're not very good measuring devices. For example, the pixels in the disk on the left are actually brighter than the equivalent ones on the right. In this image, the upper face appears darker than the lower one, but they're actually drawn with the same shade. We still see this illusion, even when it's just a gradient. Our judgment of hue is also based on the surrounding context. After a while, these flowers may appear to look red, although the pixels are actually grey. And this was the original image. When comparing image, there's another phenomena called change blindness that's particularly relevant. Something's going to change in this image. See if you can spot the difference while looking at the top right flower. And we'll change it again. It's likely that you didn't see any change. Well, for a small amount of time in between the two images, there was a grey rectangle. If we go straight from one image to the other, the differences will jump out at us. This is particularly relevant if we're comparing HDR TV to SDR, as when we change mode to switch the TV from HDR to SDR or vice versa, the TV will be blank for a while, making it harder to notice any differences. So these are things to beware of. Measure things, plot graphs, use debug visualizations. We can use various bits of equipment to measure things more scientifically. I found it particularly useful to have a camera with a fixed exposure set up on a tripod pointed at the TV. We absolutely need to aesthetically judge the final result with our eyes, but we also need to be mindful here too. It's tempting to dial up post effects and color grading, get used to them, and then dial them up some more. So let's have a look at the previous Call of Duty standard dynamic range color pipeline, as used in Call of Duty Infinite Warfare and Call of Duty Advanced Warfare. The scene was rendered in HDR with physically based shaders to a floating point buffer. This used linear values with srgb color primaries and rendered absolute scene intensity in kilonits. Some post effects were applied in this HDR color space. Then, a tone map stage ran, which exposed the scene and applied a tone map curve to convert to SDR. Exposure is a scale factor applied to linear light values to adjust their brightness for viewing. And tone mapping applies a curve to the exposed image to bring very bright intensities into displayable range. The SDR tone mapping curve we used had a number of tunable parameters to control its shape. Changing the shape of the tone map curve can produce dramatic and subtle changes to the resulting image, which could be used to apply stylistic adjustments. This was powerful, but managing the various sets of interdependent parameters can be difficult. After tone mapping, the tone-mapped colors had an srgb curve applied, so that they were ready for output on the display device. Applying the srgb curve is an example of a transfer function. In this case, an OETF, or optical electrode transfer function, that goes from optical, i.e. linear light, to electro, a signal that we can transmit to the display. With an OETF curve applied, we are now working in a display-referred color space. To display this, the TV will apply the inverse, an EOTF. The remainder of the pipeline worked in this srgb gamma space, applying additional SDR post effects, color grading, anti-aliasing, and UI rendering. So that's how our SDR image was constructed. So let's have a look at the standards for sending this to a display. If we want our SDR and HDR versions to be consistent, we need to know about these standards. And there are a bunch of standards for SDR, with fun names like ITU-R recommendation BT709. This is also referred to as BT709, or Rec 709 for short. So BT709 and Rec 709 are talking about the same thing. The SDR standards we're interested in are Rec 709 and srgb. These two standards share color primaries and white points. Because of this, changing color primaries was not as common when we dealt with just SDR rendering. SDR uses a gamma-like transfer function, i.e. a value raised to a power. Historically, this came about from CRT physics. A gamma curve lets us specify more perceptually linear values. The gradient below the diagram on the left is increasing linearly, but the one on the right, using a gamma curve, appears to have a more consistent brightness gradient to our eyes. There are lots of reasons this is useful. For example, if we have a limited number of bits for our signal, we get less banding from quantization if we're using a gamma-based encoding. So the transfer function we're all used to for PC is srgb. This has a small linear section near zero to avoid infinite gradients, but it's effectively a gamma 2.2 curve. There's another similar transfer function as part of Rec 709, which is sometimes seen when we're talking about outputting to a TV. On the left here is a picture with an srgb transfer function. On the right is Rec 709. If we zoom in on the bottom left, you might be able to see that the darks in the right-hand image have a bit more contrast than on the left. So why are there these two different OETF functions, ostensibly for PC or TV displays? And what's the EOTF function that the displays actually use? Well, sRGB is intended for viewing on a PC, which is generally in a well-lit office where there's lots of ambient light. And Rec 709 is intended for home theatre viewing, where the background lighting is dim. The different gamma values are just recommendations to account for this. So what EOTF do the displays apply? Well, it turns out it's not the inverse of either of these transfer functions. In the past, the answer was something close to a reference CRT. However, these days, panels tend to apply the EOTF specified in the DD2018 recommendation, which is a gamma of 2.4. So if we send code values to an SDR panel as sRGB, these values are actually interpreted and displayed as DD1886. Something called RGB limited range is also specified as part of Rec 709 for television signals. To provide limited range, values from 0 to 255 are literally scaled and offset and sent to the TV in a smaller range from 16 to 235. TVs are expecting this to happen and will expect values in this range. So if you send a full range value from a device to a TV, values are likely to be clipped, whereas a monitor would expect this full range signal. This isn't something we normally need to handle in our code, but it is something to be aware of and make sure that your settings are correct, especially when comparing HDR and SDR images. You should also check on various platforms whether this is getting applied when you're taking SDR screenshots or captures. Also consider that consumers might have this set incorrectly. So for an SDR image, the intensity values that we send to the display are relative. The color values we output lie in a limited range from 0 to 1, and this represents the range from the darkest value the TV can display to the brightest. But the actual peak brightness of the TV is unknown. This is like a photograph, where 0 would be black and most light is absorbed, and 1 is white, where we reflect all the incoming light. So what's wrong with these SDR standards? One problem is that we don't know the peak output intensity of the display that we're using. It's perfectly reasonable for large areas of our photograph to be white and the result to look fine and give an impression of a bright scene. But if we shine a much brighter light on the image, equivalent to using an SDR TV with a bigger peak brightness, it may have been a better choice to use a different tone map curve to put more detail into these bright areas. TVs can apply some compensation for this, but there is only so far they can go. We talked about SDR gamma transfer functions being perceptually linear, but with increased brightness, this is no longer the case, and for very bright values, our eye's response is more like a log curve. Finally, SDR only provides a limited color gamut. The range of colors we can represent, due to the location of the sRGB color primaries, is a subset of the colors that are discernible by our eyes. So HDR standards address these shortcomings. On PC, we might use srgb. This is an HDR standard from Microsoft, which uses the same primaries as sRGB, but allows values greater than 1 and less than 0 to encompass a bigger range, to give us an extended color gamut. Consoles output HDR10, and there are a number of HDR standards that are relevant. The BT2020 standard defines HDR colorimetry, and the BT2100 standard extends this with HDR transfer functions. The 2020 color primaries cover more of the perceivable colors than the sRGB primaries. This is a wide color gamut. The BT2100 standard defines what's called the ST2084 perceptual quantization, or PQ, transfer function. The idea of the PQ transfer function is to quantize our signal based on the perceived contrast of the human visual system. So this is the Barton ramp, a curve with a lot of parameters I don't even pretend to understand, that's derived from a model of the human visual system. It describes the point at which alternating between two different intensities becomes visible. Here, we are plotting this contrast sensitivity for different luminance values. Below the dashed line, things will look good. Above the line, we'll see visible banding. Here, the green zigzag line represents 16-bit float code points. This is well below the threshold, and we won't see any artifacts. Using a gamma-based encoding tracks well for dark values, but as we get much brighter values, we're wasting bits. Similarly, using a log encoding, we waste bits in the dark regions. So some smart people at Dolby did some maths and came up with the PQ transfer function, which gives a more efficient use of the bits throughout this range. PQ code values are ranged from 0 to 1. The difference from SDR is that the PQ curve represents an absolute intensity. For SDR, the values were relative, and the final brightness of the display was unknown. The linear values that PQ encodes are from 0 to 10,000 nits, which is approximately the brightness of a fluorescent tube. When inspecting PQ values when debugging, it's useful to know that a PQ code point of 0.5 corresponds to approximately 100 nits, so about the brightness of an old LCD panel. A PQ code point of 0.75 corresponds to approximately 1,000 nits, which is about the peak intensity for a number of HDR TVs. The PQ function is invertible as well, so we can transform to and from PQ easily. However, converting to and from PQ is slower than just a gamma conversion. And PQ is just a transfer function. The brightest current TVs might have a peak output of only 2,000 nits. We still need to apply some sort of tone map to go from our super bright scene-referred intensities down to this range. A TV will apply its own display mapping from PQ to its own output range, typically by applying a shoulder just before reaching its peak intensity. Before implementing the HDR color pipeline for Call of Duty WWII, we spent some time investigating the ACES color pipeline. ACES is the Academy color encoding system used in film and animation. There are reference implementations of ACES transforms on GitHub with sample input and output images. It can be useful to study the ACES code to see an example of a color pipeline, with example transformations like building color primary conversion matrices and implementations of various transfer functions. For reference, we implemented C and HLSL versions of some of the ACES transformations, using their reference images to verify that our code was equivalent. The ACES pipeline has a number of stages intended to solve various problems. Input device transforms, or IDTs, can be provided for specific models of camera to transform images into a common color space for consistency. There are color spaces for color grading, which have a high dynamic range and a wide color gamut. And the pipeline defines stages for processing and displaying output. The rendering transform takes HDR colors and applies a curve to reduce their range to something closer to displayable. The rendering transform may also apply a specific filmic look. The reference rendering transform, or RRT, is provided as a default implementation of this. Finally, output device transforms, or ODTs, are applied, which target specific output devices and display capabilities. So not all of the ACES pipeline stages were useful to us. Input device transforms were not relevant. We don't need to manage different color spaces for video editing, and the ACES output device transforms currently target specific output devices with specific intensities without the option to calibrate or adjust settings. But some of the ideas from ACES were good for us. Applying color grading in HDR solves a number of problems, and it's a good idea to have a fixed pipeline up to the final device transform. Okay, so let's have a look at what was implemented for Call of Duty WWII. We wanted our new color pipeline to produce consistent results running in HDR and SDR. We also wanted to keep a similar look to the previous SDR pipeline when running in SDR mode. We want high-quality results and high performance, and we don't want to add too much overhead for our art teams. So this was the existing SDR pipeline, and this was the WWII color pipeline. The scene rendering was mostly unaffected. We moved several stages to be applied in linear HDR color space rather than an srgb gamma space for consistency between the HDR and SDR. Color grading was also applied in HDR. And tone mapping was applied later in the pipeline in 2 stages: a fixed tone curve followed by a display mapping function to target a specific output device. This is similar to the ACES RRT and ODT stages. So we render the scene and apply HDR post effects, and then we apply exposure. At this point, we are still in an HDR and linear color space, but now scaled to expose a specific brightness range. We also apply color primary rotation from srgb to 2020 primaries at this point. This exposed linear 2020 color space is where we apply our color grading. We then apply a fixed tone curve that takes us from an HDR scene ranged intensity to something in PQ's 0 to 10,000 nits output range. The idea is that the result is something that we could output on a perfect reference display from the future, and it would look exactly as we intended. There's a lot of subtlety to defining this tone curve. What may seem like small changes can affect the look considerably. Defining the tone curve and display mapping can be more of an art than a science. We actually used something very close to the ACES RRT as our tone curve. It gives a filmic look from its S-curve shape, and the results were similar to the filmic look given by the old SDR filmic tone map curve. So this is an image without the ACES RRT applied, and this is with the ACES RRT applied. At this point in the pipeline, all the stylistic adjustments have been done, and intensity values are in a 0 to 10,000 nit range, closer to something that we can output. The display mapping then takes these values and produces color values that we can output to the connected display device. The display mapping needs to take the input and reduce the range for the output device, typically applying a shoulder to bright values. This is also where we apply the user calibration settings. There may also be a saturation adjustment. We want to desaturate bright values on lower intensity displays. The display mapping applies color primary conversion and the transfer function to convert to the output device color space. We've already applied this tone curve, so on a theoretical perfect HDR display, our HDR display mapper could just apply the PQ OETF and output the result. In reality, we may want to apply a shoulder and a toe to the values first to account for the actual black and white point of the display based on user calibration. We used the DD2018 transfer function for this. This standard is really a standard for TVs to tone map HDR inputs into their own range, but it actually suited our needs quite well. For HDR output, we used this transfer function to handle the majority of the display mapping. This function applies white and black point adjustment, specifying the min and max luminance in nits. This curve is applied in the ICTCP color space. ICTCP is a color space that gives perceptually linear intensity and hue coordinates. The DD2018 transfer function adjusts the intensity by applying an Hermite curve to the ICTCP intensity value. This is effectively working in PQ space. This intensity adjustment does not affect the hue, so finally, desaturation of bright values is applied based on how much we have adjusted the intensity. Display calibration screens were presented to calibrate the DD2018 min and max luminance. We had a separate gamma control presented to the user as brightness that was just provided in the options menu and not part of the calibration flow. For the SDR display mapper, we used a fixed curve with a linear segment and an exponential shoulder for soft fall-off. Applying this curve independently to the red, green, and blue channels causes a hue shift, as each channel saturates at different points. We controlled the amount of hue shifting by also applying this curve to just the intensity, and then blending between the hue-shifted and non-hue-shifted results. The SDR display mapper also needs to rotate color primaries from 2020 to 709. Something to note is that when we apply a color primary rotation, this should be done in a linear color space. Finally, the SDR display mapper applies the SDR OETF. We used the DD2018 transfer function for this. SDR user calibration was kept similar to the previous implementation, which only adjusted the black level. Filmic temporal AA was applied after the display mapping. One of the reasons we architected the color pipeline this way was to keep the AA operating in a perceptually linear color space without us having to retweak the parameters or do additional color space conversion. Finally, we rendered the UI. There are a number of approaches that can be used to render UI. One option is to render the UI to an off-screen buffer and to composite the results. On Call of Duty WWII, we took the approach of rendering directly to the back buffer. The existing UI shaders blended to an srgb color space. Those were unchanged when running in SDR. For HDR, we added variants of the UI shaders to scale values to a peak of 300 nits, apply color primary rotation to BT2020 color space, and convert to PQ. We also simulated how an SDR TV would have interpreted our srgb values. This did not give exactly the same results when blended as srgb, but they were close enough. Additive blending would have required a different fix, but we managed to limit the UI to just use regular alpha blending. We were lucky that this was fine for the World War II theme. When we introduced the new color pipeline, a lot of levels had already been set up with tweaked exposure settings. We wanted to try and preserve these settings in the new color pipeline. The old filmic curve parameters could be arbitrarily set per level, and changing the curve shape without normalizing the result would effectively adjust the exposure, whereas the new pipeline used a fixed curve. We added a debug command to switch the tone map mode and simultaneously modify the exposure adjustment to compensate. The adjustment was calculated by evaluating a fixed point on the old filmic curve. In the new color pipeline, we used a color lookup table called the universal CLUT in the code to apply some of the color transformations. The input to the universal CLUT is a linear color after exposure is applied. The output from this is a value that we can output to the display. We baked a number of color operations into the universal CLUT. HDR color grading, the HDR tone curve, the color blindness accessibility filter, and display mapping were all applied as part of this lookup table. Applying these expensive operations in a single lookup table was a big performance saving. This LUT was stored as a 3D texture. We used a log2 shaper function to bring the exposed HDR input colors into a 0 to 1 range that we can look up in this 3D texture. The CLUT pixels are stored in the same format as the final display buffer. The universal CLUT values were generated by an async compute shader that ran earlier in the frame. So we implemented color grading in HDR for Call of Duty WWII. The color grading was applied after exposure in a linear HDR color space. The process we used was similar to SDR LUT-based color grading, but with some changes to handle HDR values. We save a floating point HDR screenshot as a .exr file from the game with just exposure applied. We then embed an identity lookup table in the image, manipulate this image in an external tool, and then use the modified lookup table from this HDR image to apply the color grading in-game. Unlike an SDR grading LUT, where we know what color each pixel in the identity LUT represents, the HDR LUT is representing a range of HDR values, and it has an implicit shaper function applied. We added a version identifier in the image before the LUT that lets us embed additional information. This also lets us verify that no spatial operations have been performed on the image. In-game, the input to the color grading is a linear color with BT2020 primaries. Again, we used the 32 cubed LUT with a log2 shaper function to map from HDR values to the unit cube. But here the output is also a linear color with BT2020 primaries, stored in an FP16 format texture. We looked at Fusion, DaVinci Resolve, and Nuke as potential color grading packages. These are actually compositing packages, but they have good color grading tools. So this is the Fusion UI. Operations are added to a node graph at the bottom of the screen, and there are preview windows at the top and options for the selected node on the right-hand side. The grading screenshots are captured as linear HDR with BT2020 primaries. Displayed directly, they look like the image on the left. To provide a meaningful preview in the color grading package, we used a LUT to convert HDR values to SDR for display in the package. One option is to apply this LUT as the final stage of the color grade and disable it when we export. However, most packages have support for applying a view LUT that only affects the preview window and is outside the editing process. Here is an HDR screenshot in Fusion with and without our view LUT applied. To create the package view LUT, we implemented a debug option that would export the universal CLUT in a format the grading packages can use. This meant that the view LUT in the grading tools exactly matched the tone curve and the SDR display mapping that was applied by the game. The different packages support different formats of LUT file, and we used OpenColor.io to set up these for Fusion and Nuke. To support color grading live update, we implemented a script in the tools that would periodically save the contents of the preview window to a specific location. The game code would periodically look for the file, and if it found it, load it as a color grading CLUT, and then delete the file. This meant we could edit the grade in the package with an SDR preview and simultaneously view the results in-game on an HDR TV. So when we initially added the universal CLUT, everything was fine, but as we moved forward, we started to see some banding issues, as you can see in this image with the contrast boosted. We could have fixed this in a number of ways, but we ended up just increasing the size of the CLUT to 64 cubed to fix this. Some of the visual effects looked poor when we switched to the new color pipeline. This was because they were authored with a monochrome texture, which looked fine when displayed with a filmic tone map curve, but looked monochrome with a hue-preserving tone map. We could have changed the assets to fix this, for example, applying a color gradient. Unfortunately, a number of VFX assets had already been authored in this way. So we actually introduced a filmic hue shift before the display mapper for all output devices. To apply just the hue shift in HDR, we ran the SDR display mapper to provide the hue shift and then used the resulting hue at the source intensity. So how did things work out? This was the ungraded result from the previous color pipeline in SDR. And this is the ungraded SDR result from the new pipeline. The results are close to the previous pipeline, and the HDR display mapping gave us a consistent-looking image when we switched to HDR. And there's now an HDR color grading pipeline that lets us tweak this look while giving consistent results. So generally, we met all the goals that we'd set out to. This is just the beginning of our HDR story for us, and this is just one specific implementation. There are a number of areas that we're working on improving. So I think my time's up here. I hope you've gained a little bit of intuition for color spaces and color pipelines and learned a little about how we approached our HDR display pipeline. We've just scratched the surface here. There's plenty more information on this out there on all of these topics. I'd quickly like to thank everyone who helped out with this presentation and the HDR implementation, and I'd like to thank you all for coming along. Activision has a number of open job opportunities. Specifically, Infinity Ward has recently opened a studio here in Krakow. Also, please come along at 4 to hear the talk from Jorge Jimenez about updates to our temporal AA, and tomorrow to hear from Jan van Valberg about our automated testing. And please come along to our Activision booth at the Expo. If we have time for questions, I'll do my best to answer them, or please feel free to contact me.
I think we have a few minutes for questions, so let's take the microphone and come here. Yes, I think we have 2 minutes for questions. Then we unfortunately will have to. No questions. So thank you very much, Paul. And I think that the opportunity to have the further discussions with you will be great.